In this example, we have some different variables. Up until now, all the variables we've used have been x and y. We've had x for our independent variable and y for the dependent variable. And here we have s and t. S is a function of t. And you can see the equation here expressed in terms of t. This is often used, S, at least in math and physics books, is often used to represent distance or position, where something is. And it stands for spatium, which is the Latin word related to space. And it just tells where something is in space. It's also common to use x there, x as a indicator for position as well. But we'll go with s. It doesn't really matter. This is distance as a function of time. And the equation is 4.9 t squared. And we're told to find the derivative. And the derivative of the position will be the velocity. So this derived function here that we're about to find will be the velocity of the object whose position is given by this equation. So s prime will be the limit as delta t approaches 0 of s of t plus delta t minus s of t, all that over delta t. So let's put this function in and see if we can take the limit. So this will be the limit as delta t approaches 0 of 4.9 t squared, but instead of the t, we're going to put in t plus delta t and square that. And then minus s of t, which is just 4.9 t squared, and all that over delta t. So let's work this out. We have to do this squaring of the binomial before we multiply by 4.9, so we'll do that next. We have the limit as delta t approaches 0. And I'm going to keep the 4.9 out here, and then I'll have t squared plus 2t delta t plus delta t squared. And then it's minus the 4.9 t squared there, all over delta t. And then this will work out to be the limit as delta t approaches 0. And let's distribute this 4.9 t squared, and then we'll have 9.8 t delta t plus 4.9 delta t squared. And then we have our minus 4.9 t squared on the end, and that will cancel out. And all this is over delta t. And you can see the 4.9 t squared and the minus 4.9 t squared cancel out. And this leaves us with the limit as delta t approaches 0. And notice here I have a delta t in each term that remains after these two terms cancel out, and a delta t down below. So let's factor out the delta t up top. And we have delta t, and that leaves us with 9.8 t plus 4.9 delta t all over delta t, and you see the delta t's cancel. So we just have the limit, and this is our last step here. The limit as delta t approaches 0 of this, 9.8 t plus 4.9 delta t. And clearly, as delta t approaches 0, this term right here goes to 0. So we're just left with 9.8 t, and that's our answer. And you might recognize this. 9.8, you might recognize from physics, is the value of the acceleration due to gravity, at least in the metric system. So this is acceleration times time. And you might know that equation from physics. Velocity is acceleration times time. And that's always the case if your position is 1/2 at squared, where this 4.9 is half of the acceleration, half of the 9.8. So what we get here as a result of our derivation here in calculus is consistent with what we learned in physics class, as it certainly should be. Now let me make some comments on the notation here. The definition of our derivative that we've seen, and what we just saw was the limit as delta t approaches 0 of s of t plus delta t minus s of t all over delta t. That's a pretty long thing to write. It takes up a lot of time and space to write, so it's often abbreviated. And there are several ways that it is abbreviated that are all commonly used. The notation that Newton used, instead of saying s primed, he would say s with a little dot over it. And that's Newton's notation for a derivative. So s is a function of time, and s dot indicates the derivative of that, and that would be read as literally s dot. When someone's reading this out loud, they get to that and they say s dot, and it's understood that that means the derivative of s with respect to time. Another notation is this. Instead of writing all of this, you could write ds over dt, and that's Leibniz's notation. And this is a really handy notation because it turns out later on we can actually break these little things up. ds is one variable and dt is another, and that becomes really useful to be able to split those apart. Another notation is the s prime that we've seen before. That comes from Lagrange. Newton and Leibniz you've no doubt heard of as inventors of calculus. Lagrange was a European mathematician about a century after Newton and Leibniz, who made a lot of contributions mathematically, including work with infinitesimals, infinitely small quantities, which are what these things are, and also did a lot of significant work in astronomy and physics. All of these great mathematicians, Newton and Leibniz included, did significant work in physics as well, not just mathematics. And then one other notation would be s prime of t, like that. And that's, or if you're not dealing with s, if you're dealing with f, it could be f prime of t or f prime of x. And that's from Euler's notation. E-U-L-E-R. That's from his function notation. Euler, also a significant mathematician who preceded Lagrange by just a few years. Now, none of these notations is perfect. All of them fall short in some way. Newton's notation is particularly concise, but it doesn't show what the independent variable is. In this case, we're taking the derivative with respect to time. Okay, and you don't see that in the notation there. So you say this is the derivative of s, that's what the dot represents, but the derivative with respect to what? How fast s is changing relative to what? Well, when that dot notation is used, it's generally understood that time is the independent variable. So s dot is always the derivative with respect to time. So you would never have a s dot for derivative with respect to x or respect to something else. That's just understood by convention going back to the time of Newton. Leibniz's notation shows both variables. We're taking the derivative of s with respect to time, and that's useful to be able to see that. We see the change in s relative to t. And it does here suggest that the derivative is a quotient, ds divided by dt, and that's actually a useful way to think about it, but some persnickety people have a problem with that because they don't like to divide by something that's infinitely small, and we'll address that topic before long. Lagrange's notation is very similar to Newton's. It's very, very concise, but it doesn't show what the independent variable is. And then Euler's notation, it shows the independent variable, time in this place, or in this case rather. So it shows the independent variable, but it's a little bit lengthier, a little bit more clumsy than the Newton or Lagrange notation. All four of these notations are commonly used today. They've all been in use for centuries, and none of them are going away anytime soon. So it's good to know all four of these, and we'll use these different notations in this class from time to time, because you need to know all of them and be familiar with all of them. If you continue your study of calculus or study physics or engineering, you will encounter all of these notations routinely. And you should know that all of these basically mean the same thing. In fact, you could say the limit as delta t approaches 0 of delta s over delta t is the same thing as s dot, and that's the same thing as ds dt, that's the same thing as s primed, that's the same thing as s primed of t. Those are all identical in meaning.